And we'll just start in just a minute here. All right, I think we should begin. It's my real pleasure to introduce Dr. Diana Powell. She is a Sagan Fellow at the ITC at Harvard and is going to be joining the Department of Astronomy and Astrophysics at Chicago as a Neubauer Family Assistant Professor in 2023. And so I'm actually really excited that she will be part of our Magellan family. And as a matter of fact, she is visiting Chicago right now. So she's presenting from there on her way to Cambridge. Dr. Powell is an expert on extrasolar planet formation and evolution, and her work is quite broad. I think she's going to cover quite a bit of it here today in her talk, which is entitled Connecting Planet Formation and Characterization. All right, go ahead. Thank you so much for being here.
Awesome. Well, thank you, Nick, and thank you so much for having me. I'm Diana Powell, and I'm a new Sagan Fellow at the Harvard CFA. And today I'm really excited to talk with all of you about microphysical insights into protoplanetary disks and exoplanet atmospheres, which relates to the previous title of Connecting Planet Formation and Planetary Characterization. And in this talk, I really hope to demonstrate to you why we're closer than ever before to understanding the formation and evolution of planets, in part due to an ongoing microphysical revolution. And for the purposes of this talk, microphysics refers to the physics that governs the evolution of small particles in the presence of gas. And so the key question behind all of my research is, what is the origin, evolution, and nature of planets? And to address this question, I characterize planets and the planetary material and protoplanetary disks. And in particular, I use theoretical microphysical tools to peer beneath the veil of each of these stages of planet formation to uncover fundamental properties of both disks and atmospheres. And so the general picture of planet formation that has emerged looks more or less like this. So planet formation begins in protoplanetary disks, which form as the host star forms. Here, those planets form either from the accretion of solids and gas, or the gravitational collapse of material. So these protoplanetary disks really constitute the building blocks of planetary systems. Then, once the bulk of the protoplanetary disk dissipates, a young planetary system remains. And if there are gas giants present, they are initially relatively hot. And here, this second phase is not usually included in diagrams like this, but I'm doing so because this represents a distinct observational stage with unique signatures and observing strategies. And then as time progresses, the planetary system will evolve. Many of the gas giant planets, if present, will cool. Planets will find relatively stable orbits, and the planetary atmospheres will evolve. Okay, so this is the general picture. But what I really want to know is, how can we relate these disparate evolutionary stages to learn about the formation, evolution, and nature of the full complement of planetary systems? And we're really lucky to be alive at a time where each of these stages of planetary evolution is undergoing an observational revolution. And so we have these unprecedented observations of each evolutionary stage. So we can observe protoplanetary disks, such as the disks observed in high resolution shown here. And as a bonus, we can also observe protoplanetary disks undergoing active planet formation, like the PDS-70 system shown here, where you can see 2 points that are thought to be giant planets undergoing accretion. We can also observe young planetary systems directly, like the Beta Pix system shown in the bottom left. And finally, we now have observations of over 4,000 exoplanet systems, or 4,000 evolved exoplanets. And we also have detailed constraints from solar system planetary science and cosmochemistry. And so with all of these data, this is really the era to start actively connecting planet formation to planetary characterization. And the way that I approach understanding planet formation and evolution is from the perspective of chemical compositions using microphysics. And in particular, my research program focuses on using microphysical theoretical tools to determine how the chemical composition of disks relates to that of planets and vice versa. And so I'll get back to discussing microphysics in more detail in just a moment. But before I do that, let's talk about making this connection. So while the ongoing observational revolution of planets and disks represents a fantastic opportunity to connect planet formation to planetary characterization, it also represents a significant challenge. And this is because both planets and disks undergo significant evolution with time, such that it's difficult to directly connect these planets and disks in a one-to-one fashion. And so to understand some of these challenges and why the microphysical approach is crucially important, let's dive in a bit deeper. Okay, so what are we actually looking at when we observe protoplanetary disks? So observations of protoplanetary disks are primarily observations of small dust grains and some different trace gas species. So recent observations are spectacularly angularly resolved. So we can see these disks in unprecedented detail. So here I'm showing the D-sharp ALMA survey taken at 1.3 millimeter of a diverse group of bright protoplanetary disks at really stunningly high resolution. And so here you can see significant features all the way from spiral arms to smooth axisymmetric systems. But despite this level of detail, these observations are often limited due to a lack of probes of the primary disk properties, in particular the total mass in the system, and then some of the detailed but crucially important compositional properties of both the solid and gaseous mass constituents. And then this is all particularly true in the planet-forming regions of the disk. So to get more of an idea of why determining the compositions of disks is difficult, let's take a quick look at this vertical cross-section. So here the system's host star is on the right, and the disk flares out at larger radii on your left. So planets form in the disk midplane, which makes this a region of particular interest. However, in the midplane, the ice particles are moving radially, which affects the midplane composition. And this radial motion can eventually cause the ice to reach hotter regions of the disk, where they lose their volatile material back into the gas phase, again altering the composition. And at the same time, the gas in the disk is being mixed around and changing the radial composition. And not only are these disks constantly in a non-equilibrium state, but to top it all off, there's gas present in the upper regions of the disk that can be optically thick, such that you can't see emission from the midplane directly. And all of this is especially true in the inner regions of disks, where we know that planet formation is common. Okay, so determining useful compositions of disks is difficult, but what about planets? So what are we actually looking at when we observe young and evolved planetary systems? So a primary source of compositional information about planets comes from atmospheric observations. And an example of some of the data for these observations are shown here for young planets on the left and evolved planets on the right. And so on the left, I'm showing a collection of emission spectra for directly observed planetary mass objects. And on the right, I'm showing a collection of transmission spectra for 10 hot Jupiters, which are highly irradiated Jupiter-like planets. Despite the detail we can observe in these objects' atmospheres, these observations are often hindered by opacity sources, such as clouds and hazes, that can obscure compositional features and other planetary properties. And so what we're probably looking at are atmospheres that look something like these atmospheric slices. So these atmospheres are covered in clouds. And the clouds can either be low altitude, such that we can observe some unobstructed regions of phase space, or high altitude. And the high altitude clouds will completely obscure signatures of atmospheric composition. But even when clouds are low altitude, they can obscure planetary signatures, they can alter observed gas phase abundances, and they can influence planetary radiative transfer. And then, in addition to the complicating presence of clouds, atmospheres also evolve. And then also, we can best observe planets in orbital regimes where it's difficult to observe protoplanetary disks directly, which can significantly complicate our comparisons. So in both cases, many of the complications with determining chemical compositions boils down to a need for a better understanding of microphysical processes. And in this context, I'll remind you that I use microphysics to refer to the evolution of small particles and the presence of gas. And so many of the key common processes are shown here. And in the case of atmospheres, microphysics governs the evolution of clouds. And in disks, microphysics governs the evolution of small, icy, or rocky solids. And by the end of this talk, I hope that you'll see how microphysics applies in several different contexts and is crucial in understanding these systems. Okay, so to make the connection between protoplanetary disks and planetary atmospheres, we need better physical models to interpret current and upcoming observations. And I'll argue in this talk that microphysics will be important in making this connection. And in fact, microphysics may well be the key to understanding the origin, evolution, and nature of planets. So I'll start by talking about some of the initial work that I've taken towards tying planet formation to planetary characterization. So I'll start by talking about planetary atmospheres with a focus on clouds. I'll then move on to discussing fundamental properties of protoplanetary disks, such as the total amount of mass present in these systems. And then I'll hopefully have enough time to talk about bringing these two techniques that I've used to study atmospheres and disks together through a discussion of the evolution of carbon monoxide in protoplanetary disks. So let's talk about clouds. So we all have some intuition about clouds on Earth. But clouds are important beyond Earth and are in fact the dominant opacity source in most planetary atmospheres. Clouds are important tracers of atmospheric physics, such as mixing and transport. Clouds regulate the planetary climate through regulating radiative transfer and chemistry. And clouds must be understood when determining atmospheric abundances. Also, often the clouds in an atmosphere are the only thing that we can see. So it's therefore an absolute necessity that we understand clouds when we're interpreting planetary atmospheres. And clouds appear to be abundant in substellar atmospheres. So here on the left, I'm again showing a collection of transmission spectra of 10 hot Jupiters, where many of these atmospheres have damped spectral features and flattened or sloped optical spectra, all of which is indicative of some optically thick absorber of stellar photons like clouds. Clouds may also have been observed directly in the atmospheres of brown dwarfs. So brown dwarfs are substellar in mass with radii roughly equal to that of Jupiter and effective temperatures that are similar to some giant planets. And crucially, brown dwarfs have atmospheric properties similar to many giant exoplanets. And in the middle here, I'm showing emission spectra of 2 brown dwarfs with this broad absorption feature in the infrared that's not quite captured by the model shown here. And this is thought to be caused by silicate clouds in their atmospheres. And then clouds are also thought to contribute to observed spectral variability. So on the right here, I'm showing emission spectra of the same brown dwarf at 2 different times, where you can see that the amplitude of the spectra can vary significantly. So clouds often dramatically impact observations of substellar atmospheres. And I approach the study of clouds using microphysics with the community aerosol and radiation model for atmospheres known as CARMA. So CARMA is a well-tested code that has been applied to nearly every planetary body in our solar system with an appreciable atmosphere. So CARMA works on an Eulerian grid of particle size and altitude, where particles are allowed to grow and move into larger bins as well as evaporate and move into smaller bins. And then particles can also move vertically along this grid. And karma is a particularly powerful tool because it starts from first principles and then calculates the fundamental cloud properties that shape observations. So namely, the fully resolved cloud particle size distributions of various cloud species as a function of time. And so on the right here is a general picture of how karma operates. So here I'm showing altitude in the atmosphere as well as temperature and pressure. So the condensable gases are mixed upwards from a reservoir in the deep atmosphere until they reach a point where the gases become supersaturated and cloud particles form via microphysical processes. These particles can then themselves be vertically mixed or settle gravitationally. And before I talk a bit more qualitatively about the microphysical processes that we consider, I want to emphasize that this model is not a black box. So we've engineered every single key microphysical component and have really carefully considered every aspect of cloud formation that's considered in this framework. So we aren't looking at a black box, we're looking at physics. And there are three key microphysical processes of cloud formation that we consider. And so all of these processes depend on the atmospheric conditions as well as other key properties. So the first process is nucleation, which occurs when a supersaturated background gas nucleates onto a seed particle. And there can also be homogeneous nucleation, where a gas nucleates without the presence of a seed. And then whether a species nucleates homogeneously, heterogeneously, or not at all depends on the species-specific material properties. So in particular, the surface tension of a species, which determines the nucleation rate and is in the exponential term in the equation here. Then condensation occurs when a condensable molecule diffuses along a path and interacts with a cloud particle, and condensational growth occurs. So this process is often limited by diffusion, so just the time it takes for the condensable molecule to reach the cloud particle. And finally, clouds can also grow via coagulation, where two cloud particles collide, forming either a larger spherical particle or an aggregate. And this process is often limited in our simulations by the particle number density. Okay, so here's a primer of some of the results that I calculate with karma. So I'm plotting the mass density of condensed cloud particles as a function of particle size and atmospheric pressure. And so here, each of the different colors indicates a different cloud species. And so as you can see, each cloud species forms at different times and has different particle sizes and vertical extents in the atmosphere. And our results also tend to reach a steady state, as there's some variability in cloud properties, which may very well be real, like the climate cycles that we see on Earth or Venus. And I'm quite interested in this variability, but for the remainder of this talk, I'll be showing time average solutions. Okay. And so with results like these, I can uncover the likely impact that clouds have on observations that we gather of planetary atmospheres. And I'll again emphasize that quantifying this impact is crucial for our understanding of planetary properties. So we can answer key questions, such as the impact of the cloud particle size distribution on the observed spectra. And so on the top right here in black, I'm showing a model transmission spectra for a hot Jupiter with my fully resolved cloud particle size distribution. And then on the same plot in blue, I'm showing the transmission spectra if I take an average cloud particle size for each cloud species while conserving the total cloud mass. So as you can see, both the amplitude and the shape of the transmission spectra changes between the two cases. And this is particularly true in the optical and near the broad cloud absorption features in the infrared. And so this indicates that understanding the cloud particle size distribution is important when interpreting observed spectra. And then because this framework also considers barriers to cloud formation, we can also predict which cloud species dominates the observed spectra. And so in the bottom right here in black, I'm showing a different model transmission spectra for a different hot Jupiter, where we include the opacity from all the cloud species that form. In gray, I'm showing what the transmission spectra would look like if there were no clouds. And then in the different colors, I'm showing what the spectra would look like if we only consider the opacity from a particular cloud species. And so in this case, we see that silicate clouds dominate the cloud opacity across a broad wavelength range and really shape the spectra. And in addition to impacting spectra, clouds may also serve as probes of planetary properties, such as their interior thermal structure. So here I'm showing emission opacities as a function of wavelength and atmospheric pressure for a planet that has the same upper atmosphere structure, so same temperature structure in the upper atmosphere, but different internal thermal structures. And here the dotted white line indicates the location where the clouds become opaque. And so for the high entropy planet with a hotter interior, clouds are opaque as high as 0.1 bar in the atmosphere. But for a planet with a lower entropy interior, the clouds only become opaque at around 10 bar. So clouds may thus be able to serve as probes of planetary interiors, as they are sensitive to planetary properties across different atmospheric scales. And with this framework, we can also predict how clouds will look at different locations on a given planet. So here I'm showing cloud particle mass densities as a function of particle radius and atmospheric pressure, where each color represents a different cloud species. And for this case, we're looking at cloud properties on different locations of a relatively hot Jupiter. So these planets are tidally locked, such that they have a permanent day side and an extreme insolation gradient across the planet. And this insolation gradient drives a super-rotating equatorial jet that operates in the atmosphere that operates to reduce this gradient, but it does so less efficiently at hotter temperatures when re-radiation dominates. So relatively hot Jupiters tend to have very hot day sides, a hot eastern limb, a cool night side, and then a cool western limb. And to me, the atmospheric inhomogeneities on these planets, as well as their high temperatures, make them exciting laboratories for understanding cloud physics. So we think that many different cloud species should form, and they should do so differently at different locations on the planet. And indeed, on the hotter east limb, we find that clouds form higher in the atmosphere and grow to relatively small sizes. On the cooler west limb, more cloud species form. They do so deeper in the atmosphere and grow to relatively large sizes. And then the polar regions represent an intermediate between these two cases.
Diana?
Yes.
A quick question about interpreting these simulations. How should we sort of, in our minds, visualize what these different clouds are? Are they all mixed together, or are these clouds of different species separated on the surface?
Yeah, so you can imagine a few different things, but in our models, we tend to have one cloud species, TiO2, form first, and it has a really low surface tension. It can form homogeneously. It doesn't need the presence of a seed. And then after that, different cloud species will form on top of the TiO2 grain. So it's relatively straightforward to put into our simulations that you could have cloud species layering on top of each other. And that might be the case. So it'll be interesting to see once we can look at the optical properties of clouds and the infrared, these broad absorption features. But why we think that clouds may appear to be more clear, more one species in type, is because really heterogeneous nucleation, so the process of one species forming on another one, is often harder to do than condensational growth. So one species, like once you form an iron cloud, you keep forming more iron on that species. It's easier than having an iron cloud form and then forming silicate on top of it. So that assumes that we have our understanding of cloud microphysics right. So definitely it would be improved with empirical data to compare to. But that's the thinking here. So they really are species with a different core element, but then a mantle of something like chromium or silicate. And so we can translate these cloud properties into transmission spectra that look significantly different in both amplitude and shape between the east and west limbs of the same hot Jupiter. So in black, I'm showing the calculated transmission spectra on the east and west limbs. In gray, I'm showing the east limb cloud-free transmission spectra. And then in blue, I'm showing the opacity continuum due to clouds. So here on the west limb, cloud opacity is significant across a very broad wavelength range where it flattens the observed transmission spectra. But on the east limb, clouds contribute to this muted and sloped optical spectra and this broad absorption feature in the infrared due to silicate and aluminum clouds, which collaborators and I will probe in James Webb Cycle 1. And then there's also this intriguing clear window around 3 to 10 microns that could allow us to peer through the clouds. And so to really understand the nature and composition of planetary atmospheres, we'll be greatly rewarded by looking at these planets in 3D. So as you can see here, the east limb gives us much more information than other locations on the same planet. And with these mock spectra, we have shown that clouds are likely to enhance observed atmospheric inhomogeneity on the limbs of hot Jupiters, in certain cases in a way that should be clearly visible with JWST, demonstrating that James Webb will offer us novel ways of observing the 3D nature of planetary properties. So here I'm showing 2-scale limb radii differences for a hot Jupiter in the case of clouds on the top and for a cloud-free atmosphere on the bottom. So the cloudy atmosphere has distinctly asymmetrical limb radii that's significantly more inhomogeneous than the clear atmosphere, which has some limb asymmetry as well, just due to temperature differences on the limbs. And we've developed a tool for probing this atmospheric inhomogeneity cheaply using James Webb. And then I'm also working on interpreting observations of exoplanets in emission, reflection, and transmission using 2-dimensional models of microphysical clouds, where we calculate how cloud properties change as clouds are vected along the super-rotating equatorial jet of a hot Jupiter. So here I'm showing condensed cloud mass of different cloud species as a function of planetary longitude and pressure. And using these models, we can robustly determine the impact of clouds on high-resolution observations and exoplanet phase curves. And these models will become increasingly more useful with the launch of JWST, which will allow us to uncover atmospheric trends across populations of planets. And so an example of one such trend that has already been observed in hot Jupiters is shown here. So as their planetary equilibrium temperatures increase, the day-side temperatures also increase linearly. However, the night-side temperatures for this diverse range of hot Jupiters remains roughly constant, even as their day-sides heat up significantly. And so we've modeled the clouds on these atmospheres and found that constant night-side temperatures on hot Jupiters is a natural outcome of the abundant production of spectrally active silicate clouds. So these silicate clouds dominate the atmospheric opacity on the night sides. And so even accounting for changes in vertical mixing with changes in global circulation that occur as a function of equilibrium temperature, we show that we're really seeing across all of these planets on the night side, we're looking at the silicate cloud top, so the top of the silicate clouds. Okay. So I've discussed the importance of understanding clouds and substellar atmospheres, which is important in constraining planetary properties. And now I'd like to switch gears a bit and turn our attention to protoplanetary disks, which are the locations of planet formation. And I'll start by talking about the interesting question of how much total mass is present in these systems. And so the question of how much mass is in protoplanetary disks is fundamental for planet formation and evolution. So the amount of total mass in the system influences the ultimate mass and composition of formed planets by affecting the evolution of solids and gas that eventually make up the planetary system. The total disk mass also regulates specific planet formation processes. So particularly the class of processes where the amount of gas, which makes up the bulk of the disk mass, affects the evolution of the solids. And so the question of how much mass is present in these systems needs to be answered so we can get a handle on the initial conditions of planet formation and how these might vary from system to system. Okay, so the most common tracers of protoplanetary disk properties are dust or different trace gases, such as CO gas, as these are relatively easy to observe. And due to a lack of direct probes of the main mass constituent, H2 gas, previous measures of disk mass have relied on some tracer to H2 ratio. However, we know that processes such as grain growth and drift should alter the dust to gas ratio from the typically assumed interstellar medium value. And now several lines of evidence also suggest that gas CO, particularly in the commonly observed upper disk layers, is depleted or missing in disks. And so this begs the questions: how can we measure total disk mass without an assumed tracer to H2 ratio? And also, what is happening to all of the CO? And really getting to the bottom of these questions is of the utmost importance for understanding disk physics and other disk properties, which will allow for an improved understanding of the initial conditions of planet formation. And so I began addressing these questions by considering multi-wavelength observations of disks in the millimeter. So here I'm showing a visualization of observations of the disk around TW Hydra. So these are all images of the same disk, and you can see that it appears smaller in radius at longer wavelengths. And to introduce some terminology, I refer to the maximum radius in which there's emission at a particular wavelength as a dust line. And as others have suggested, these observations may be signatures of particle drift. And I'll take a step back for a moment to talk about the two main processes that can limit particle growth in disks. And here I'm showcasing work done by my student, Elizabeth Gunnerman, who has just started graduate school at Harvard. And so here in the shaded regions of phase space, particles are unlikely to reside in disks due to barriers to their continued growth. So the process that's the most relevant in the inner disk is fragmentation, which depends sensitively on the assumed particle material properties. So fragmentation may be significant for a range of particle sizes throughout the disk, or may only be relevant for a narrow range of particles in only the innermost disk regions. However, as I'm interested in the dust lines in the outer disk, where particle growth is limited by drift, let's talk about drift, the process of drift, in a bit more detail. Oh, and I'll skip through this, but I'll just say fragmentation also depends sensitively on the composition of the grains. And there's intriguing outcomes for how particles could grow in disks because of this, as composition changes throughout the disk. Okay, but particle drift. So particles drift in disks because the gas feels an outward pressure gradient that causes the particles to feel a drag that removes some of their angular momentum and causes them to drift inwards towards their host star. And so I'll take just a little bit of time walking through this timescale, since it will lead to the key equation for this portion of the talk. So the drift timescale of a particle is given by its orbital distance r divided by the velocity difference between the gas velocity and the local Keplerian velocity. So that's this term v naught. And then there's the stopping time parameter, tau s, and that's because the particles are neither quite at the gas speed nor at the Keplerian speed. And so we observe small particles that are relatively well coupled to the gas with stopping times less than 1. And in this regime, larger particles with larger stopping times drift faster. And so we can write the stopping time in terms of standard disk parameters and then rewrite the drift timescale. And so this timescale that I'm showing here is exactly the same as what I've written above and is just rewritten in terms of the total gaseous surface density in the disk. And you can understand why drift depends on the gas surface density, because if you have more gas, then there's more gas drag, and that will change the stopping time, so how well coupled a particle is to the gas for a fixed particle size. And if we rearrange this equation like this, we see that we can derive the total disk surface density as a function of radius if we know the rest of these quantities. So in particular, if we know the maximum radius and which particles of a given size are present. And notice here that for a fixed particle size and fixed radius, a larger surface density means that you have a longer drift timescale just because you're better coupled to the gas. So thus, if we have some knowledge of the particle drift timescale, we can use this method to derive the total disk mass. And so to motivate my choice for drift timescale, here I'm showing a dust evolution simulation that shows the surface density in solids as a function of particle size and radius in the disk. And in particular, I want you to focus on the dashed red line here, that indicates the maximum size that a particle can grow to before it drifts inwards. Okay. So as you can see, in the outer disk at late times, particle growth is limited by drift and fragmentation becomes less important. So on the outer disk, the maximum particle size at a given radius is therefore set by particles whose growth timescale equals the drift timescale. So that's actually how I've drawn this red line shown here. And then also, if you look at a particular distance, the maximum particle size is reduced over time as larger particles drift inwards. So we can therefore expect that the largest particle size at a given radius at a given time will be the particle size with growth and drift timescales equal to the age of the system. So this is the particle that's had the entire age of the system to grow up to the maximum size that it can before it's about to drift inwards to the host star. And we won't use this right now, but I want to mention the fact that the dust to gas ratio is also decreasing with time. Okay, so because the maximally sized particle has a drift timescale that's roughly the age of the system, we can use this information to now determine the surface density at a given radius if we know the maximum particle size at that location. So we can infer the particle size if the observed wavelength corresponds to the primary particle size contributing to the observed emission at the disk outer edge. And we can measure the disk size to determine the radius in which these particles are the maximally sized grains. And this method allows us to derive the disk surface density without assuming a tracer to H2 ratio, because we only care about how fast the particles drift, which depends primarily on their size and not on how many particles are present. Okay. And so here on the right is a quick visual summary of this new picture of protoplanetary disks. So large particles of size S1 are present throughout the disk until they reach a radius where their drift timescale is equal to their growth timescale, which is roughly equal to the age of the system. And if you were to look at a disk at an observing wavelength approximately equal to S1, then you'll see a disk with this radial extent. Then the same is true for smaller particles of size S2 that will extend throughout the disk until they reach a radius where their timescales are equal. And again, for even smaller particles, S3, which extend to a further out radial region in the disk. And if you were to look at the system at an observing wavelength comparable to size S3, you would see a much more radially extended system. And I've applied this model to 7 protoplanetary disks with previous millimeter observations that show decreasing disk radial extent with wavelength. And here I'm showing some of these observations for 3 out of the 7 disks in our sample. And as a technical aside, this is how we're actually measuring the disk outer edge, which is an important measurement as it's one of the fundamental quantities in our modeling. So that's the maximum radius in which particles of a given size are present. So we develop an MCMC method for finding the disk outer edge through modeling the disk interferometric visibilities using a Newkirk profile. And so on the left here, I'm showing a sample set of modeled visibilities. And on the right, I'm showing a model surface brightness profile. And here my method for finding the disk outer edge, marked by the blue line, is robust, even if there are brightness dips caused by substructure in the disk. Okay, so here I'm showing the total gaseous surface densities for the disks in my sample. The black points are the surface densities derived from dust lines, and the red or blue lines are previously published surface density profiles. And what I've done here, well, so these profiles, the previous ones, were derived from CO emission or the combined multi-wavelength observations of dust. And what I've done here is to normalize these profiles to match the dust line derived surface densities. And so if we had many more points from dust lines, we could just directly fit the profile shapes, as shown here in the dashed line for the disk around DUAR 25. But right now we can match previous profiles quite well. And notice that these profiles do not all have the same slopes, and the dust line derived points are not all straight lines, and instead follow the curves of these profiles. And this really did not have to be the case. So for example, FT tau and TW hydra have different profile shapes, but for both, the dust line points match the previously published profiles. And so all of this is what makes me encouraged that this model is doing well. And so we can now place these dust line derived masses in context. So here on the left, I'm showing total gaseous surface densities in black for 2 of the disks in my sample, compared to previous tracer-derived surface densities and the minimum mass solar nebula, which represents the minimum mass required to form our solar system. So the disks in our sample are 9 to 27% of their host stellar masses, which is significantly more massive than the minimum mass solar nebula, which is about 2% of the sun's mass. These disks are also 2 to 15 times more massive than estimates from optically thin dust emission, assuming an interstellar medium dust to gas ratio. And for the 3 disks in our sample with resolved CO emission, our estimates are 3, 40, and 115 times more massive than previously published, indicating that CO depletion is not uniform across different disks. So these results indicate that dust is a more robust tracer of total mass because we uncover a reduced gas to dust ratio that is roughly consistent across our sample, while the CO to H2 ratio varies more strongly. And I'll come back to this later in the talk. Okay. And so here I'm plotting the Tumor-Q stability parameter as a function of radius in the outer disk. And so a Tumor-Q parameter less than approximately 1 is where you would start gravitationally collapsing under your own self-gravity. And so all the disks in my sample are stable to gravitational collapse, except for 1 disk which approaches the limit of Tumor-Q stability. And interestingly, that disk's morphology also shows some indications of gravitational instability in high-resolution images. But note that all of the disks in our sample have low Q values at certain radii. And so we think that when you form disks, they're accreting because they're marginally unstable, and this marginal instability might be helping to raise spiral arms that throw material onto the star efficiently. And so we still think that all of that is going on. But then after this early phase of star formation, you really need something like MRI or disk winds to kick in to drive further accretion. And it's a big mystery how disks are able to accrete efficiently at late times. But maybe if some disks are actually close to gravitational instability, you do not need a lot of these accretion processes to be happening, because at least some disks, so at least the bright massive disks in my sample, seem to maintain much of their mass. And in our modeling thus far, it is not required to know an expected dust surface density. But given our results, we can now use models of coagulation to compute the dust surface densities, since we know that the maximally sized particle at a given location has a growth timescale equal to the age of the system. And so here I'm showing surface densities for the disk FT tau, where the blue line is the total gaseous surface density derived using our dust line method, and the solid black line is the observed dust surface density. And here the dashed lines are dust surface densities derived using analytic and numerical treatments of particle coagulation. And so for the disks in our sample, we derived depleted dust to gas ratios around 10 to the minus 3, so an order of magnitude less than the interstellar medium value, which is a common outcome of models of grain growth and drift. And so in my models, the dust drifted into the inner disk where it undergoes further evolution, but you can also paint a consistent picture with some of the drifting dust being incorporated into planets over time. And it is worth noting that in these models, the disks formed with an initial dust mass that is a factor of 10 greater than is presently observed. And also being able to constrain the dust and gaseous surface densities using this method can allow us to empirically constrain the dust opacity, which is particularly exciting because the dust opacity remains one of the largest sources of uncertainties in studies of protoplanetary disks. And so we can learn a lot using this model that I haven't talked about here. So things from the aggregate nature of the solid particles that we observe to the nature of the disk morphological features. But overall, here's this new picture of disks, where they may be more massive than previously appreciated. So the total dust mass is the same, but the total gas mass is an order of magnitude larger. And these qualitative changes to models of protoplanetary disks have significant implications for theories of planet formation. And this is particularly true for any process where the amount of gas affects the evolution of the solids. So that will be affected by this picture. And then I also want to emphasize that our model indicates that there is more dust mass at early times, which helps bring agreement between the discrepancy in observed disk dust masses and the observed mass of extrasolar systems. Okay. So we've discussed the total mass in disks, but really what is happening to all of the CO gas in these systems? And we really want to know the answer to this question because CO has been used as a tracer for a broad range of fundamental disk properties, which could be biased if we're assuming that there's more CO relative to H2 than reality. And also because CO is a primary carrier of carbon in protoplanetary disks and is thus important when we talk about planetary inheritances. And so to answer this question, I'll combine the two methods that I've used so far in this talk. So modeling clouds and modeling disks. And this is a short section, but let me know about time constraints. Okay, so it's not just my modeling that indicates that CO is depleted in disks. So on the left here, I'm showing the CO abundance in the disk TW hydra as a function of radius as compared to the abundance that we would expect from observations of the interstellar medium. So you can see that CO gas appears to be significantly depleted. And then the same appears to be true if we look at large samples of disks. So here on the right, I'm showing an ALMA survey of disks in Lupus, where the disks span several orders of magnitude in dust mass, but have fairly constant gas masses estimated from CO. So in short, we observe much less CO in disks than we would expect or than would be predicted using previous disk models. And to address this problem, I've coupled my model for protoplanetary disk properties with an adapted version of the models that I use to study cloud formation in exoplanet atmospheres. And in this context, I'm modeling the formation of ice on dust and disks. And in particular, the nucleation and growth processes in the scheme include the Kelvin effect, which quantifies the stability of ice particles through considering the strength of the molecular surface bonds. And so I like to think about this effect in terms of geometry, where an ice molecule on the surface of a small grain will not be able to molecularly bond to as many neighbors as it would on a large particle. And thus, in short, the Kelvin effect causes large particles to nucleate and grow more easily. And the particle sizes are important here because they regulate the level of depletion of gaseous CO. So if we approximate the disk temperature structure as shown here on the left, where the disk, so this is the vertical structure of the disk, where it will be roughly isothermal until it reaches a height where surface layer heating is efficient. So in the midplane, the disk is cold enough for ice to form on dust grains. So there will be a region of the disk where ice is stable, and then a region where evaporation could occur. And if the ice particles that form in the midplane are small, then they can be lofted to the upper regions of the disk and evaporate such that CO gas is not significantly depleted. On the other hand, if an ice particle is large, it can deplete the CO gas in the midplane. And so that's what I'm showing here on the right. So once the initial abundance of CO gas, shown in solid black, is depleted in the midplane, as shown in gray, there will be this steep vertical concentration gradient, which will eventually be smoothed by vertical diffusion. And this would ultimately lead to a depletion of CO in the observed upper layers of disks, as shown in solid red. And so this is the so-called cold finger effect, which can lead to a large depletion of CO gas in the upper disk. But the particles and gas in the system evolve radially as well as vertically. So at early times, gas will be depleted much faster in the inner disk, where vertical gas diffusion is faster. And then with time, CO gas is increasingly depleted in the outer disk as diffusion has time to operate. Then in the inner regions of the disk interior to the ice line, ice particles will drift inwards until they reach a warm enough region of the inner disk where they release their volatile content. And then this causes there to be an increased abundance of CO gas in the inner disk that can then be accreted onto the host star. And so to quickly walk through the evolution of CO in disks, in the outer disk, CO gas is continually mixed down towards the disk midplane, where efficient ice formation occurs on large particles. These large particles drift inwards towards their host stars. And then once these ice particles drift to the hotter regions of the disk, they release their volatile CO back into the gas phase, and some interesting cycling of material occurs around the ice line. And then there will also now be an enhanced abundance of CO gas in the inner disk that will be accreted onto the host star over time. And with this modeling, we find good agreement between our results and observations, as I'm showing as in the small plots, B through E, around the big plot here. And in our modeling, we find that this process depends strongly on diffusion, so the amount of mixing in the disks, which contributes to the observed variance of CO depletion in different disks. So in the large plot here, you can see that the amount of observed depletion in the outer disk depends on the amount of diffusion that is operated in the lifetime of the disks. And I'll note that this process is applicable to other volatiles in disks, such that the microphysical processes of ice formation both regulates the observed abundances of CO gas and is crucial in determining the radial composition of protoplanetary disks. And using this model, we're able to constrain the solid and gaseous CO inventory at the disk midplane where planets form, and constrain the bulk disk diffusivities and mixing characteristics, and resolve inconsistencies in estimates of the disk mass. So these are three crucial parameters that control planetary formation. Okay, so that was a lot. I've talked about understanding substellar atmospheres using cloud microphysics, and I've discussed uncovering fundamental properties of protoplanetary disks using particle aerodynamics and ice formation. And so I'll leave you with these takeaways from the talk and take any questions. Thank you so much.
All right, wonderful. Thank you so much. I see a lot of
Yay!
cartoon hands. Thanks, Dan. That added up some fun to the end. Okay, does anybody have any questions? And while people are pondering that, I'll start off early in the talk. When you were showing the models, you made a statement about how you're interested in the time variability, although you were only going to consider the static situation. Could you comment on how it just seems like time variability is so hard to measure? And so curious how you think this might be useful and interesting. Thanks.
Yeah, so the time variability here is particularly interesting to me because it depends primarily on the mixing in atmospheres. So with something like a 2D cloud model, you could predict where you think clouds are. We have some estimates of the horizontal wind speeds in a planet, so that can be inputted into the model. And then the primary driver of the variability is the vertical mixing, so KZZ. So I think that the timescale of the variability scale than really the amplitude of what we're seeing could be telling us a lot about the vertical mixing and how much is present in atmospheres, which is notoriously difficult to observe. So that's why one of the main reasons I'm really excited. So getting some empirical determination of vertical mixing. Although it also tells us other things. So once you have more detailed information, you could tease out some other microphysical characteristics. That one sounds a lot harder though.
All right. Wonderful. Okay, so why don't we just go in order on my screen? Andy is up first and then Anna.
Hi, that was amazing. I just have a really basic question. So do you expect with your model, this condensation and then evaporation when the grains move into the inner disk, do you expect any differences that you could check? For example, isotopic, like presumably this was C12O16, but would you expect any difference in the C13O16 abundances that you might measure?
That's a really great question. I don't have the answer to you yet, but I do want to see how how we'd expect differences in isotope logs to evolve in this picture, and how that compares to predictions from CO self-shielding. So that's something I absolutely want to look into, but don't quite have the answer to just yet.
Okay. Thank you.
Go for it, Anna.
Right. Thanks for the talk. This is really awesome. I actually had a follow-up on Nick's question, and it was about the time variability. And so it sounds like what you're calculating here is some sort of I don't know, stable solution. And I was just wondering how stable the atmospheres are on external some sort of external perturbation, for example, solar wind, or maybe something more like a coronal mass ejection or something like that?
Really good question that I haven't spent much time thinking about myself, but you could imagine that having a huge impact on cloud formation. So we know that different photochemical drivers of cloud formation are incredibly important all the way out to Jupiter and our solar system. So I could imagine something like a coronal mass ejection doing really interesting and wild things to a planet. So maybe even lose some mass, and in that outflow you get clouds forming in a way that's visible. So I think that's interesting.
And I guess as a follow-up, is karma, the code that you're using, is it sort of flexible enough to include these sort of like different boundary conditions to explore that?
Yeah, so I definitely think it could be sensitive enough to do different boundary conditions. That's a really good point. It is unfortunately slow enough with modern computers now that coupling it to something like a large general circulation model, which I would like to do self-consistently, is just out of reach. But hopefully in the next 5 years or so, then I could imagine a really interesting, like full 3D simulation of something like you're talking about. But in the 1D or 2D sense, that's something that, yeah, that could be looked into.
Great, thank you.
Okay, and then we've got 2 more questions. Gwen, why don't you go first?
Sure, that was a fabulous talk, Diana. So I'm curious about these observations of protoplanetary disks. I was wondering what the prospects are for getting larger samples. I take it that they're quite expensive, the sets of observations that are required. So have all of the sort of disks that are viable for these kinds of observations been done, or is it possible to do more?
That's a great question. So I do think that everybody has, so that the D-sharp disks or the big, bright, massive disks are the ones that we're really getting super high detailed information of. I think that as we move to things like maps and surveys where you're looking at different molecules, there's still some work to be done there as well. And then I think we're starting to push towards other disks, but it's harder. So you're not getting quite the same data quality, but we are now looking at larger surveys of disks and smaller disks to see if this holds true for a broader sample. Yeah, and I think once with the ALMA upgrade, that should also be more probable. But yes, I do think that the data quality that I'm really excited about for disks, it's still hard to do for the vast majority of objects in the sky, especially for multi-wavelength observation. So that's really difficult when you push outside of these big, bright, massive disks.
Perfect, thank you so much.
Okay, and I apologize. I don't know if I'm going to pronounce your name right, but Bade, you're up next.
Hi, yes, that's actually correct pronunciation.
Okay,
Thanks.
great, thank you.
Thanks, Diana. That was a very clear talk, especially I appreciate it coming from a galaxy evolution background. My question is about the CO depletion in the protoplanetary disks, and whether there's information about the stellar metallicity or the gas metallicity that is kind of maybe varying in the different samples that you have, and whether this is a dominant subdominant effect to the diffusion.
Yeah, that's a great question. So certainly with the disks that I've modeled so far, so these 4 disks, the 4 of the most well-studied disks in this way, it definitely, you can paint a consistent picture with having an average interstellar medium abundance that you're inherited. But I do know from the star formation community that CO also is very interesting in molecular clouds and possibly in the ISM as well, to the extent where you might expect CO to vary the inheritances that you get from a disk. So in that sense, this modeling is quite degenerate with that. So if you inherit less CO, then you need less diffusion. We are now looking at some other ways of probing mixing in disks, whether that's from looking at the settling of grains to see how much mixing there is, or from looking at velocities of carbon monoxide gas in the upper disk, which also gives you somewhat of an indication of how much mixing is there in disks. So far, these results are quite consistent with that. So all consistent with a relatively average abundance of CO being inherited initially, but it is degenerate in this modeling.
Oh, okay, interesting. Thank you very much.
All right, wonderful. Thank you so much, Diana. That was great. One last round of applause. If anybody would like to chat with Diana, feel free to email her or just email me. And thanks again. That was great.
Thanks so much. Thanks for having me.
Thank you. That was fantastic.
That was really great. Thank you.
Wonderful talk. Thanks so much, Diana.
So nice.
Yeah, thank you so much.